In the next decade, the moon might stop being a symbol of exploration and start becoming the most valuable mining site in human history. Buried inside the lunar soil is a rare isotope called helium-3, a potential fuel for future nuclear fusion that could power Earth with almost no radioactive waste. And right now, two superpowers are preparing to go after it: the United States and China. Not with astronauts swinging pickaxes, but with fleets of autonomous robots crawling across the moon's surface. By 2030, the moon may become the center of a new geopolitical race, one that could reshape global energy, space policy, and the balance of power on Earth. So how real is this lunar mining revolution, and who is most likely to win it? The moon looks empty: gray dust, cratered plains, an airless desert. But beneath that dust lies regolith, a layer of pulverized rock created by billions of years of meteor impacts. Inside that regolith is something extremely valuable: helium-3. Helium-3 is incredibly rare on Earth. Our planet's magnetic field blocks most solar particles that carry it, but the moon has no magnetic shield. For billions of years, particles from the sun have been embedding helium-3 directly into the lunar soil. Estimates suggest the moon could contain over 1 million tons of helium-3. And if fusion reactors using helium-3 become practical, just 1 ton could theoretically power a major city for an entire year. Suddenly, the moon stops looking like a desert and starts looking like the biggest untapped energy reserve in human history. Why is helium-3 such a big deal? Because of nuclear fusion, fusion is the same process that powers the sun, combining light atoms to release enormous amounts of energy. Most fusion experiments today use deuterium and tritium, but that reaction produces large numbers of high-energy neutrons, which create radioactive waste and damage reactor walls. Helium-3 fusion could change that. A deuterium-helium-3 reaction produces mostly charged particles instead of neutrons. That means much less radioactive waste, more efficient energy capture, potentially safer reactors. In theory, it's one of the cleanest energy sources imaginable. There's just one problem. Helium-3 is almost non-existent on Earth, which means if humanity wants large amounts of it, we'll probably have to go off-planet. And that's where geopolitics enters the picture. The United States and China are both building long-term lunar programs. The US, through NASA's Artemis program, plans to return astronauts to the moon and eventually build a sustained presence near the lunar South Pole. China, together with Russia and several international partners, is developing the International Lunar Research Station. Both programs aim to establish permanent lunar infrastructure in the 2030s, and while the official focus is science and exploration, the strategic implications are obvious. The first nation that develops reliable lunar resource extraction could gain access to rare materials, control over key lunar locations, leadership in space industry. In other words, FESA. The moon may become the next frontier of economic power. But there's a major obstacle. The moon is an extremely hostile environment. Temperatures swing from plus 120 degrees Celsius in sunlight to minus 170 degrees Celsius in darkness. There's no atmosphere. Radiation levels are high, and the abrasive lunar dust can destroy mechanical systems. Sending large numbers of human workers would be extremely expensive and dangerous. So instead, the mining workforce of the moon will likely be robots, specifically autonomous rover swarms. These machines would operate almost entirely on their own, digging, heating, and processing lunar soil. Here's how it might work. Rovers collect regolith and transport it to processing units. The soil is heated to around 700 degrees Celsius. Trapped gases, including helium-3, are released. The gases are separated and stored. Tankers eventually transport the material back to Earth orbit. Because communication with the moon has a delay of several seconds, these machines need high levels of autonomy. They must navigate terrain, avoid hazards, and coordinate with other robots without constant human control. Think less like a remote-controlled vehicle, and more like a self-organizing robotic mining colony. The most likely location for early lunar mining isn't random, it's the south pole of the moon. This region has several major advantages. First, some crater rims receive near-constant sunlight, providing almost continuous solar power. Second, nearby permanently shadowed craters contain water ice, which can be turned into oxygen, drinking water, and even rocket fuel. And third, these regions are relatively stable environments for long-term bases. That's why multiple countries are targeting the same general area. Which raises a difficult question. Who actually owns the moon's resources? International space law, particularly the Outer Space Treaty, says no nation can claim territory on the moon. But it doesn't clearly define ownership of extracted resources. That legal gray zone could become one of the biggest political debates of the next decade. There's an important reality check here. Helium-3 mining is still largely theoretical. We don't yet have commercial fusion reactors that use it. Extracting it from lunar soil would require processing massive amounts of regolith. And transporting material back to Earth would still be extremely expensive. So lunar helium-3 mining might not happen exactly the way early enthusiasts imagine, but something else probably will. Building infrastructure on the moon, power systems, autonomous robots, mining equipment, and transportation networks will create an entirely new space economy. Helium-3 might just be the first reason to build it. For most of human history, the moon was just a distant object in the sky. Then in 1969, we reached it, and in the coming decades, we might start using it, not just for exploration, but for energy, industry, and resources. By 2030, autonomous robots could already be preparing the first lunar mining sites, quietly digging through gray dust in a place no human has walked for decades. And the outcome of this race may shape the future of both space and Earth, because the next great energy revolution might begin 240,000 miles away. If you enjoyed this deep dive into the future of space industry, consider subscribing for more videos on emerging technology, geopolitics, and the science shaping our future. And one big question: if lunar mining becomes real, should any country be allowed to own resources from the moon? Let me know what you think in the comments.